All right, folks, I'm ready to get started. Welcome back, everyone. Welcome back to the end. I think it's the 12th week. I think we're in the 12th week, and we have about I don't know, 3 or 4 weeks left of class, and then like a week of finals. So we're certainly at the end-ish of the semester. Definitely, there's more to cover and more assignments and whatnot to get completed, but we're there. We can see the end. Just a reminder that Tuesday we are not meeting, so just remember that. I'll send an email on Monday or Sunday, and I'll remind all of you just so that you don't forget. Yeah. No, I'm not going to be here at all that day, so I won't have office hours, and yeah, 3:10 won't meet either. Yeah. So just keep that in mind. All right, well, we are almost at the end of Chapter 9, which again is the first of the last 4 chapters that we're covering for the last part of the course. It deals with the basic oligopoly models. Again, oligopoly is a setting in which firms are operating amongst a few other firms. Everybody has a large market share in the market. They have a large piece of that pie. And so because of that, they share a downward sloping demand curve, which means that every time somebody makes a decision, the entire market moves along that curve, and therefore any decisions made by one firm affect the decisions by the other firm, etc. And so therefore it makes the analysis more complicated. It makes the management of these companies that operate in these markets more complicated. And so this chapter covers 4 different models that help us to sort of understand how to best maneuver different possible scenarios that firms may find themselves in this context. And so each of the models differs based on the assumption that the firms are making about what their rivals are going to do. And oftentimes those assumptions are going to be based on whether or not the firms are competing on a price level, meaning that they are competing price-wise, setting a price, and then responding to prices set by rivals, and then coming to some sort of equilibrium price for the market based on that process, or they are competing on quantity choices. So they are choosing quantities, their rivals are choosing quantities in response to them, etc., or maybe they're doing it at the same time. So like there's different dimensions of competition that these firms can engage in, which again changes the possible outcome for the market, changes the analysis that we engage in here. So again, we've been covering a couple of them. We covered the Sweezy, we covered the Cournot, we covered most of the Stackelberg last time. I'll briefly go over that again. Then we'll go over what's called the Bertrand oligopoly today. It's a very simple case. And then we'll just kind of do a comparison of the 4 really quick, just kind of see how those market outcomes differ based on the nature of the competition that these firms exist in each of these settings. And then we'll do a quick sort of mention of this thing called the contestable market, where we look at how competition may not happen only within a market, but in terms of the firms that are trying to enter the market, they can also be competing to enter the market, and those existing if there's certain conditions, then it'll stop other firms from getting in, of course, if there's barriers to entry. But if there aren't barriers to entry, then the threat of firms entering a market will actually change the way they behave in the market. So we'll talk about that. We'll talk about how that looks. And then we're going to start Chapter 10, which deals with game theory. So game theory is a way of studying situations where there's interdependence in decision making, where it doesn't have to be economics, it's just anything where like your decision is based on what rivals are doing and rivals' decisions are based on what you do. I'll briefly talk about the fact that game theory was used like throughout the Cold War era to sort of try to figure out what the best course of action is against the Soviet Union, when everybody was kind of building up their nuclear arsenals, and there was a threat of nuclear holocaust. So I'll briefly talk about that. Anyway, lots of applications for game theory, but certainly a very relevant application in what we're talking about in oligopoly, where again there is interdependence in decision making, and so firms are essentially engaging in games, or we can look at it that way. And with game theory, we kind of take situations and kind of make them into a game, and then establish like what are the likely outcomes based on the strategies that players can play, and other kind of characteristics we can identify by using that method. And of course, the method as introduced here is going to be very simple relative to what it actually looks like in practice. But again, it's just meant to give you an idea of how these things work. But we'll go through several applications in this chapter and several different type of cases that one can sort of apply game theory to, and how those different circumstances in those cases change the outcome of the game, and ultimately allow us to gain some insights into how firms are able to sort of work their way around the limitations that are placed upon them in these markets, again, where there's interdependence, and that is sort of ultimately kind of like a shackle on them in terms of their ability to enact their market power in the way that they want to enact their market power, in the way that will, again, maximize their profits. So we'll just briefly do an overview of games and strategic thinking, and then we'll do we'll start covering what's called the simultaneous move one-shot games, in which firms make decisions at the same time and they only interact once. But then we'll look at other cases next week on Thursday when we meet again. Again, Tuesday I'm not coming. I'm not going to be here all day on Tuesday, but so Thursday when we meet again, we'll start covering the other cases where there are maybe multiple times that the firms are engaged in competition, not just a one-time situation, and also when firms aren't making their move at the same time, but they're making them sequentially. So like one firm makes a move first, and then another firm reacts, like in the Bertrand oligopoly setting that we talked about. All right, so today we'll finish chapter 9. I'll open up the mini paper and the homework for that. I won't make them do both of them until next Wednesday night. So because we're not going to meet till Thursday, I'll give you a little bit more time to work on that stuff. Yeah. So we already covered them, and I'll briefly cover them again today. Yeah. We will compare oligopoly models that we covered in the chapter. Not the Sweezy one, because the Sweezy one is slightly different in terms of like how we go about understanding it. Like it's not necessarily based on like the assumption of like what your rivals are going to do in terms of output. It's just meant to sort of highlight the fact that you're going to have a kind of weird demand when you assume that your rivals are going to lower their prices in response to your price reductions, and not increase. And not increase their prices in response to your price increases. But yeah, it does fall under the basic oligopoly models, but we won't be covering it in the comparing oligopoly setting. Other questions that you'd like me to address before I move forward with the material? Anything in general? So just remember, this is chapter 9, mini paper, and then chapter 10. And then you have to look at the syllabus to see if there's gonna be enough time to do chapter 11, because there might not be enough time to do chapter 11 mini paper, because I think the paper is due then on the Tuesday after we finish the chapter, which will give you like 4 days to write it. I mean, I guess I could set up a submission option for you, but it's not a good idea for you to write a mini paper at the last minute. You should be working on the paper itself, just kind of cleaning it up, not actually writing it, cleaning it up that weekend to turn it in. And again, if you've written the 3 mini papers already, then all you have to do is write an introduction, a conclusion. The introduction basically states you are a manager of this firm. This is the situation. Just briefly summarize your case, just briefly. You don't have to talk a lot about it. Just like, this is what's going on. These are the 3 areas that I've highlighted in my analysis to kind of give insight or, provide prescriptions for what they should do. Briefly summarize those. The introduction should be about a page, and then you just throw the 3 papers together. It's a good idea at the beginning and end of each one to kind of or at the end of beginning and end of each one to kind of just add a little verbiage to kind of make it flow from one section to the next, and then of course write a bit of a conclusion that basically mirrors the introduction. It doesn't have to be a full page, but anyway, enough so that you kind of like are summing up all the points that you made throughout the paper, and then you're done. So that last part that I mentioned shouldn't take you more than like 1 or 2 hours. So if you've already done the mini papers, then it should not be a problem for you to just like get this paper, the final paper, finalized and ready to be turned in with minimal time and effort. So make sure that you are at that point by that weekend, the weekend before you submit the paper, versus like you are scrambling to write new things and just like think through things again. Like that's not the time to be doing that. The time to be doing that was the entire semester, as you had opportunities to write mini papers, and you still do. And you still have the open chapter mini paper submission option, so it's not too late for you to really spend some time to get some decent papers written if you haven't done anything. I'm not talking to the majority of you here, I'm going to assume, because the fact that you come to class regularly tells me that you're likely on top of things, and so I'm sure the majority of you have at least knocked out a few of these, if not all of them. So good. But I'm sure there's always that group. There's always that group in my class. They just like wait till the last moment, the last 3 options, and I don't know why they do it, because in the end their papers don't turn out that great. But hey, everybody's free to make the decisions that you want to make about how you go about doing the things that you do in your life, and all I and anyone else can do is just kind of suggest what you should do to maybe help yourself to improve. But again, like life is about learning. You make decisions, either they work out or not, and then you kind of learn things. So anyway, so the paper, the other thing to note is that the open chapter mini paper submission option, it has a deadline. I don't know what it is. I forget what I put it, but I know that it's coming up. So just keep that in mind. Check Moodle. There's the option. April 30th? Okay, so April 30th is when I said it. It's coming up in a couple of weeks, so it's still up. It was still available for a couple of weeks. And so take advantage of it. But that will not be one of the options you'll have that last weekend. So keep that in mind. And I did that because I don't want people writing everything the last weekend, because it's just a bad idea. All right, anyway. So that's the paper, and it's coming up. And again, 20% of your grade overall. You get 6% of that just by turning in your mini papers. So if you're missing any of those, it's a bad idea. You're just kind of hurting yourself for no reason. So just make sure that you get things done. Alrighty. And of course, submitting the paper, as I mentioned before, and I'll mention a few more times before the deadline, I need a hard copy and a digital copy. Digital copy is for me to check your word count and for me to have an archive so that I make sure that people aren't turning in papers from other semesters. I can go back and check. So that's that. All right. All right, Chapter 9, Basic Oligopoly Models. Again, we're just covering the stuff we covered already before I jump into the final part of the chapter. Oligopoly, again, refers to a situation where there's relatively few large firms in an industry. We covered the Sweezy oligopoly, in which there's, of course, a few firms serving the market, defining it as an oligopoly. The firms produce a slightly different version of what everybody else produces, a differentiated product. Each firm believes that their rivals will cut their prices in response to price reductions, but not increase prices in response to price increases, which creates a kinked demand curve, which creates a weird sort of marginal revenue curve. And of course, barriers to entry exist. So this is the weird marginal revenue curve, and because there's this weird marginal revenue curve, there's a range over which, if marginal costs were to drop, that the firm should not do anything. They should not change their output, whereas normally marginal cost is set equal to marginal revenue that dictates the amount that a firm will supply. If costs drop and therefore marginal costs drop at that level, marginal costs would be below marginal revenue, which means that the firm would want to increase their output. So that's the natural response to costs dropping. But again, in the Sweezy setting, because of this assumption, there's a range over which that should not happen. And if one does do that, then it will hurt their profits. So it's just something to, it's an important insight that we can gain from just studying the that kind of setting in the way that we do in the Sweezy model. All right, the second one we looked at was the Kuno oligopoly. In the Kuno oligopoly, again, few firms serving many consumers, oligopoly. The firms produce either slightly different versions of what everybody's selling or the same thing, a homogeneous product. Each firm believes that rivals are going to hold their output constant if it changes its output, and that is the main assumption here that sort of defines the setting. Everybody's choosing outputs at the same time. So everybody's choosing, let's say everybody's in the oil market. So everybody's deciding at the same time how much they're going to supply in terms of oil to the market. And so nobody knows exactly how much everybody else is going to supply, and everybody's making the decision at the same time. But everybody understands, that everybody kind of has like a similar cost structure, and everybody knows what the demand curve looks like. So you can come up with these reaction functions, which again are rules that allow a firm to set an optimal output in response to what their rival is likely to set. And so normally, if that wasn't the case, if you didn't have rivals you had to depend on and take into consideration, you would just set your optimal output based on setting marginal revenue equal to marginal cost. The same thing is done in this setting, but marginal revenue has your opponent's output in variable in the marginal revenue equation, and therefore you have this extra variable, your opponent's output, which then you need to take into consideration in this marginal revenue equals marginal cost relationship, which then allows you to derive your output as a function of your rival's output, called the best response or reaction function. So we graphed them first, and we saw, putting quantity of firm 1 in the x-axis and quantity of firm 2 on the y-axis. This is firm 1's reaction function. This is firm 2's reaction function. Where they intersect is the equilibrium for the Kuno oligopoly setting. So that's the set of outputs that is going to maximize both firms' profits, given, again, the nature of demand and the nature of their costs. And then we solved, of course, for the Kuno reaction functions by taking the perspective of a firm on the market. So by taking the perspective of a firm on the market, you basically set the other firm's output as constant. So taking firm 1's perspective on the market and taking firm 2's output as constant, you put firm 2's output in the constant. So this is the inverse demand function with the two quantity variables corresponding to the two outputs that the two firms will choose, which comprise the total output in the market. Firm 1 takes firm 2's output as constant, then it just looks at its marginal revenue by doubling its slope there. That's where that 2 comes from. And then it sets it equal to marginal cost, which we assume was 0 in the problem. And then you have this relationship now that allows you to derive your output Q1 as a function of Q2 via some algebra. And so we did, and therefore this is firm 1's reaction function. Firm 2's reaction function is symmetric to firm 1's because they both have the same marginal cost. If they didn't, they'd have different reaction functions. Where those two reaction functions intersect, that is where the Kuno equilibrium outputs are determined, and we do that mathematically by just looking at our two reaction functions and then just doing a system of equations analysis using two equations to solve for two unknown variables, firm 1's quantity and firm 2's quantity. So again, you just plug in firm 2's quantity reaction function to firm 1's reaction function, then you just solve for firm 1's reaction, Kuno equilibrium output, and then you plug that into firm 2's reaction function, and that gets you firm 2's equilibrium output. And then to solve for the price in the market, the price is going to maximize both firms' output. You plug both of their outputs into the inverse demand function, and that gets you to the price for that market. Now, we also used this framework of ISO profit curves to identify the fact that there exists an incentive in oligopoly settings for firms to work together in order to increase their profits. So this is the Kuno. So obviously, it's a little bit ugly right now because everything's on here, but I did animate this last time. So if you don't really understand what's happening here, make sure you go to the last lecture and kind of take it one step at a time so you really understand what this means. But anyway, this is the Kuno equilibrium output. These are the ISO profit curves associated with that. But this area here represents outputs where both firms could make higher profits. So This is the collusive output. Collusion is like firms working together. If both firms were to supply here, which is less than they would supply under the Cournot setting, therefore limit the output, raise the price, they could both earn higher profits. In the US, that's illegal, so they can't actually do that, but they try to do it anyway, and when they try to do it, they can't enforce their arrangements because, again, those arrangements are illegal. And so because they can't enforce the arrangements, there is actually a further incentive for firms to cheat on the agreements that they make to collude and make even more profits. So the firm that cheats can make even more profits and wind up on a higher ISO profit curve, but the firm that is cheated on winds up on a lower ISO profit curve than they would have been if they'd just done the Cournot thing and just let the market kind of result in its natural outcome. And so this highlights the fact that there is that extra layer of complexity to these interactions. It's not just interdependence that complicates the analysis, but also the fact that there is this incentive for firms to work together, and then also there is an incentive for the firms to cheat once they decide to work together, which is what requires us to, again, have more approaches to kind of trying to understand how to best maneuver these settings, which is why we now will be studying the next chapter, which is game theory, which kind of helps us to understand how to best maneuver that setting. Yeah.
On the PDF file, it's going to come out like this, correct? But on the PowerPoint, it will.
Yeah, exactly. You have to look at the animated one. Yeah. And those like they'll open up full screen, but if you don't want it to open up full screen, you can open it within PowerPoint, and then it won't open up full screen. But anyway, you can look at the video as well. All right, so that's the Cournot setting, and then of course we jumped into the Stackelberg setting, and the difference between the Stackelberg and the Cournot setting was only one small difference, and that is that there is a first mover, a leader, somebody that gets to choose their output first, instead of like in the Cournot where everybody sets their output at the same time. In a Stackelberg setting, one firm sets their output first, and then everybody reacts to that. The way they react to that is in a Cournot fashion. So the followers have a Cournot reaction function that they use to figure out how much they should supply in response to what the leader does. The leader knows that their followers are going to do that. And so therefore the leader, when choosing their output, has to take into consideration what their followers are going to do by incorporating their Cournot reaction functions into their perspective on the market. And by doing that, again, they both wind up maximizing their profits to the best extent possible. So let's again cover that demonstration problem that sort of highlighted the mechanics of how to solve for the outputs of both the leader and the follower, and ultimately then the prices charged in the market. So suppose the inverse demand function for two firms in a homogeneous product Stackelberg oligopoly is given by this equation here. Again, Q1 represents the output by the leader, Q2 represents the output by the follower. And the cost functions for the two firms are this one here. We keep it simple. There's just a variable cost, which means that marginal cost is equal to 2. And both firms have the same cost. Firm 1 is the leader, firm 2 is the follower. So we need to solve for firm 2's reaction function, knowing that firm 2 will react in a Cournot fashion. So we solve for firm 2's Cournot reaction function the way we did in the last section. Then we solve for firm 1's output, who will be the first mover that needs firm 2's reaction function in order to figure out what it should do first. So that's why we have to solve for firm 2's reaction function first. So we'll solve for firm 1's output. Then we'll solve for firm 2's output once the market knows how much firm 1 decides to supply, because again, they have a first mover advantage. They decide how much they're going to supply first. Once that's clear to the market, firm 2 reacts to that via their reaction function. And then finally, once the two outputs are determined, we can solve for the market price. All right, so what is firm 2's reaction function? Well, again, we need to take the perspective of the market from firm 2. That means they're taking firm 1's output as constant. So 50 minus Q1 is the constant. And then you have minus Q2 as a residual demand. So you double the slope on that. So you get 50 minus Q1 minus 2Q2 as the marginal revenue for firm 2, set it equal to firm 2's marginal cost, which is equal to 2 there. And now we've got, of course, this relationship that allows us to solve for firm 2's output as a function of firm 1's output. That is basically, again, the rule that tells firm 2 how to best respond to what firm 1 does, so that no matter what firm 1's doing, firm 2 can always respond to that and constantly be maximizing its profits. So doing a little bit of algebra here, subtracting this term from both sides, and then dividing both sides by -2, we get to firm 2's Cournot reaction function to be 24 minus 1/2 Q1. All right, so that's firm 2's reaction function. So now we choose firm 1's output, which again is the first move that is made in the market by the leader, the Stackelberg leader. So firm 1's output. So here is the inverse demand function. So what firm 1 wants to do is they want to incorporate what firm 2 is going to do in terms of how it reacts to what firm 1 does. So it needs to incorporate firm 2's reaction function into its inverse demand function. So plugging in Q2 for Q2 in the inverse demand function gets us to 50 minus Q1 plus 24 minus 0.5 Q1. And then now we've got minus Q1 plus 0.5 Q1, which leaves us with minus 0.5 Q1, and then minus 24, so 50 minus 24 is 26. 26 minus 0.5 Q1 is basically the demand that the Stackelberg leader has now derived that will allow it to maximize its profits, knowing how its rival is going to respond to it. And now it's just your standard monopoly solving for their optimal quantity and price, and we're not solving for profits, but you could. Not price either, because we have to, I'm sorry, yeah. We're just going to solve for firm 1's output, which essentially, once they've incorporated what the other firm is going to do in response to them, can approach the market like a monopolist would. So they set their marginal revenue equal to marginal cost in order to optimize their profits. So here is the marginal revenue for the leader, 26 minus Q1. Marginal cost is equal to 2 for firm 1. So 26 minus Q1 equals 2, and then just solve for Q1 gives us the Stackelberg leader's output, in this case to be 24 units. And then to solve for firm 2's output, we have to plug in firm 1's output into the best response function for firm 2. So plugging in 24 in there gets us to 12 for the follower. So that is firm 2's output. And now that we have firm 1 and firm 2's output, we can solve for the market price, which by plugging in Q1 and Q2 into our inverse demand function gets us to 14 bucks. So that's the price they both should charge in order for both of them to maximize their profits. Is there any questions on how this was done? So it's just about keeping it organized in your mind, like, you know, one approach versus another based on the assumptions being made in the market. The mechanics of solving for all this stuff is not that complicated. If you've been plugged into the course and you understand, you know, everything that we've talked about up until this point with respect to how firms make optimal decisions. And so it's just taking it a couple of steps further to, again, reflect that extra sort of layer of complexity that these firms face in these markets. All right, so in these markets, in the Stackelberg market, like in the Cournot market, like in all oligopoly settings, price, well, not all oligopoly settings, actually. Price will exceed marginal costs in a Stackelberg oligopoly, meaning industry output is going to be below the socially efficient level, so you're going to get some deadweight loss. You're going to get some mutually beneficial transactions that don't happen in order for these firms to be able to, you know, make extra profits in the market. So that's what that translates into. All right, so let's look at this final one, this final case, the Bertrand oligopoly. The Bertrand oligopoly actually winds up being the best one for consumers, and it winds up resulting in the best outcome in terms of prices, but the worst outcome for firms, because you essentially wind up in that perfectly competitive outcome, the perfect competition outcome, where firms are forced to set their prices equal to marginal cost, and therefore they earn zero economic profits in the long run. So an industry is characterized as a Bertrand oligopoly if there are few firms in the market serving many consumers. The firms produce identical products at a constant marginal cost. Firms engage in price competition and react optimally to price changes by competitors. And consumers have perfect information and there are no transaction costs. So it's price competition that defines this market, much like the Sweezy oligopoly. But the Sweezy oligopoly is slightly different in that, again, it's like the assumptions are being made about what rivals are going to do in response to price changes. And the conditions aren't exactly like this, where the firms have marginal costs that are constant. Anyway, so firms engage in price competition and react optimally to prices charged by their competitors. So again, like there isn't like a very specific rule on like I'm going to lower my price in response to my rivals' price reductions and not increase my price in response to my rivals' price increases. Like it's not like a very clear-cut rule like that. It's just basically I'm going to undercut my rival as much as I can in order to get as much of the market as possible. And again, consumers have perfect information means that everybody knows that everybody is selling the same thing. Everybody knows that the quality of what is being sold is the same across sellers, and that everybody that wants to buy something has a lot of options to buy those things from more than just one seller. But of course, barriers to entry do exist in this market, which is not the case in the perfectly competitive setting. So from the point of view of the manager, a Bertrand oligopoly is undesirable. It leads to zero economic profits, even if there are only two firms in the market. From the point of view of consumers, Bertrand oligopoly is desirable. It leads to the same outcome as a perfectly competitive market. Again, because consumers have perfect information and there are zero transaction costs, and because the products are identical, all consumers will purchase from the firm charging the lowest price. All right, so suppose that firm 1 were to charge a monopoly price, so like the highest price possible in any market. Firm 2, by slightly undercutting firm 1, would capture the entire market and then make positive profits, while firm 1 would sell nothing. But of course, firm 1 could retaliate by then undercutting firm 2's price and thus recapturing the entire market. So again, essentially, they wind up in a price war, and the price war ends with both of them lowering their prices as much as possible, essentially to the point where they set their prices equal to their marginal cost. They can't obviously charge below that because they would be operating at a loss in those units. So Bertrand oligopoly and homogeneous products lead to a situation where each firm charges marginal cost and zero economic profits are made by the firms. All right, so it's a very simple case. But it is one that, again, highlights the sort of complexity of these markets. The fact that you do have some ability to have market power, but because the firms aren't able to work together, they wind up in price wars that wind up getting them to this outcome where they are making zero economic profits. Now, there's sort of ways of maneuvering around the price war situation because all the firms understand that they will result in this outcome where they make zero economic profits and their prices are equal to marginal cost if they do engage in a price war. And so via game theory, we can sort of analyze how firms are able to sort of not explicitly make agreements, but like implicitly kind of understand the nature of the market they're in and sort of be working together without actually talking to each other about it, because they know what the result will be, and they know it will hurt everybody. And so even without making explicit agreements, they're sort of able to make agreements to not engage in price wars. Yes?
This is solely based on the assumption that both of them have the same cost.
Yeah.
To produce. Because if one had less, then obviously that one could bring that price down
Lower than the other one.
lower, and that one, right?
Right, exactly. So we're talking about markets where, like, again, this is a homogeneous product market, so the thing being sold is the same, so nobody can do anything special with it. And generally things like that, like, it's going to be very easy for firms to enter those markets because they can get what they need to enter those markets, and therefore they will have the same cost because what they need to enter those markets is going to cost the same to everybody. But there are barriers to entry, so maybe you need to be like of a certain size in order to operate in these markets. That is what keeps other firms out. All right, so let's compare these oligopoly models and their outcomes. Suppose the inverse market demand function is equal to 1,000 minus Q1 plus Q2, and the cost functions of each firm are identical and just given by 4QI, where I indexes the individual firms in the oligopoly. All right, so for the Kuno market, the profit function for the individual firm is P times Q minus the cost. So revenue minus cost is just your standard profit, and then we've inserted the inverse demand function for price. That's why it looks kind of ugly, but it's your standard profit equation. The reaction functions for the Kuno oligopolis in this market are going to be 498 minus 1/2 Q2. I'm not going to solve for them because I've already solved for this stuff enough times. If you want to solve for them, please go ahead and do so to get some practice. Anyway, these are the reaction functions for the two Kuno duopolists in this case. Solving the two reaction functions gets us to output of 332 each for each firm. So total output in the market is 664, which if you plug that into the inverse demand function gets us to a price of $336. And plugging those values into the profit function reveals that each firm earns a profit, in this case, of $110,224. All right, so that's the result for the Kuno setting. Let's look at what happens in terms of the market outcome in a Stackelberg setting. So with these demand and cost functions, the output of a Stackelberg leader, if it's exactly the same market, but a firm gets to go first in terms of choosing their output, then the Stackelberg leader will wind up supplying 498 units, which is definitely higher than the 332. So immediately you see that the leader is able to supply more than they would if they didn't get that first mover advantage. The follower takes this level of output as given and produces according to its reaction function. And therefore the follower winds up producing 249 units, which is less than, of course, what the Kuno duopolists get to supply. Again, because the leader gets to go first, the leader winds up getting a bigger chunk of the pie of the market. Total output does increase though for the market because there's a leader. So because there's that first mover advantage, it actually makes a more efficient market outcome. You get more mutually beneficial transactions happening in the market, so there's less deadweight loss than we had in the Kuno setting. Given the inverse demand function, this output yields a price of $253. So we see that the price is significantly lower than in the Kuno setting as well. So again, just by having that first mover advantage, that lowers the price in the market, making it better for consumers. The Stackelberg leader, of course, winds up doing better, but the Kuno follower winds up doing worse. The profits of the leader are $124,000, which is higher than the profit that each firm in the Kuno setting makes. And the follower's profits are going to be $62,000 roughly, which is definitely significantly less than the Kuno setting. So we see that profits are hurt for the follower, but the leader does wind up profiting quite a bit just from having that first mover advantage. So the firms collectively wind up making more profit, but the market winds up doing better because, again, we wind up with a situation where the price is lower and there's more units being transacted, so more people get to buy the things they want. So the leader does better in a Stackelberg oligopoly than in a Kuno oligopoly due to its first mover advantage. The follower earns lower profits in the Stackelberg oligopoly than in the Kuno oligopoly. All right, the Bertrand equilibrium is simple to calculate, right? It's the perfectly competitive outcome. So recall that firms engage in Bertrand competition and end up setting price equal to marginal cost. Therefore, price equals marginal cost, which is equal to $4, and profits are 0 for each firm. So we see that if the firms are forced to engage in price wars, then the consumers wind up winning as much as possible by paying the smallest amount in the market, which is ultimately what all markets should result in from the standpoint of efficiency, which is what economists are always kind of looking for. We're looking for markets to serve as many people as possible and ultimately serve society the best possible, because deadweight loss does hurt society. Profits of firms do help society because profits are firms are part of society, but again, deadweight loss means there's consumer surplus that's lost. Individuals, consumers, wind up being hurt because of market power. And of course, transactions that could happen don't happen. But in a Bertrand oligopoly, when firms are forced into a price war, then you're going to get that perfectly competitive market outcome, which we're always hoping markets will lead to. And total output will be the greatest amount possible. We'll have 996 units transacted in those markets. And then, of course, there is that last option, collusion, where the firms are working together. The firms are working together. They're essentially working together as a monopolist. So you're going to get the worst market outcome with a monopolist. All right, so when firms collude, total industry output is the monopoly level based on the market inverse demand curve. Since the market inverse demand curve is equal to P equals 100 minus Q, the marginal revenue is going to, of course, equal 1,000 minus 2Q. The marginal revenue function assumes the firms have made an agreement or are acting together as a single profit maximizing firm, which is what collusion is all about. Setting marginal revenue equal to marginal cost yields, just doing your standard manipulation, an output level of 498. So under the collusive outcome, if the firms are able to somehow get together and make agreements and work as a monopolist, we get the lowest amount of units being sold in the market. We get the highest price. We get $502, significantly higher than the Cournot, definitely twice as much as Stackelberg, and yeah, ridiculously more than the Bertrand setting. So this is basically this just highlights like the extreme sort of opposite ends of the spectrum that these firms can operate in, and the kind of outcomes that you can have in a market, just given like that variation in how much market power firms have. So definitely monopolists are able to charge significantly higher prices, and of course the monopolist will wind up making as high a profit as possible, which in this case happens to be the same amount as the Stackelberg leader gets to make too. So we see that the Stackelberg leader winds up benefiting from the market the way a monopolist does in terms of profits, but we get a better outcome with the Stackelberg situation when you have a first mover advantage and the firms are choosing output levels. But again, this is all about sort of helping you to understand like how these different oligopoly settings work and the kind of effects they can have on a market, just given the nature of the competition that these firms engage in. So if you become a manager in an oligopolistic market, it's important to recognize that your optimal decisions and profits will vary depending on the type of oligopolistic interaction. And finally, let's look at this kind of weird case of a contestable market. So we've emphasized strategic interaction thus far amongst existing firms in an oligopoly. Strategic interaction can also exist between existing firms and potential entrants into a market, leading to a Bertrand-like outcome. A contestable market is a market in which a single firm exists, but there's another firm, a potential entrant, that is free to enter the market whenever it chooses. So there's one firm operating, and there's always the threat of another firm coming in. A market is contestable if all producers have access to the same technology, consumers can respond quickly to price changes, existing firms cannot respond quickly by to new firms entering the market by lowering their price. So it takes them a bit of time to adjust their pricing. and there's no sunk costs. There have to not be any sunk costs in the market as well. If these four conditions hold, then incumbent firms that exist in the market already, have no market power over consumers. So in a contestable market, you will, again, get that perfectly competitive outcome. The equilibrium price will correspond to marginal cost, and the firms will earn zero economic profits. So the reason for this result is as follows. If existing firms, if that one firm that's in there charges a price above their marginal cost, then a new firm could immediately enter the market with the same technology and charge a lower price. Since the incumbent, the existing firm, cannot quickly respond by lowering their price, then the entrant would get all the incumbent's customers by charging the lower price. Incumbents are disciplined by the threat of entry by the new firm. So just simply the fact that someone could come in and threaten to basically drive you out of business stops a firm from being able to, enact their market power. In this case, we're looking at a single firm. So you're talking about a monopolist, but they cannot operate as a monopolist because the market is contestable. So an important condition for a contestable market is the absence of sunk costs, as I mentioned. So suppose the incumbent firm, the firm existing, is charging high prices, and that a new entrant, so the new firm that is threatening to enter the market, calculates that it could earn $70,000 by entering the market and charging a lower price than the existing firms. So suppose that to enter the market, the firm, though, this new firm that wants to enter the market, has to pay, let's say, $20,000 in sunk costs. They have to maybe invest in some certain materials that are perishable, maybe, like they'll just rot within a week or so, who knows. Something that they have to invest in will not be able to be retrieved. Like that money will be gone once they pay the money. So the incumbents, the existing firms, cannot lower their prices quickly, so the entrant may earn some profits early on, but those profits will not be enough to offset the loss of the $20,000 once the incumbent is able to then lower their price as well, and therefore making it not useful, not even worthwhile for any firm to try to enter the market. And that's why there have to be no sunk costs in contestable markets. Alrighty. Let us jump into Chapter 10, game theory inside oligopoly. So again, game theory is an approach that's been developed over the last few hundred years in different forms, but it certainly became very relevant to the world when, we passed post-World War II, when, obviously the Soviet Union helped the Allied powers to win the war. We sort of divided up the world in terms of like the way that we economically interacted, right? Like the Soviet Union was communist. They were a command economy where you had the government basically making all decisions for the economy. And then you had, of course, the US and other Western nations that were, market economy based. And there was this ideological conflict. But there was also not a direct conflict because we had worked together to kind of, solve the problem of Hitler, etc., and Japan. And so we weren't directly at odds, but that ideological sort of schism that we had was at the source of this Cold War that we had, over the course of like 40 years, in which there wasn't a hot war, right? We weren't directly engaging in war, but if there were wars going on, like we were kind of in there on both sides, and those wars were generally related to this ideological difference that we had in terms of our economies. Anyway, because of that, everybody kind of was building up the nuclear arsenals, which again, nuclear weapons, as you all know, were developed during World War II and then kind of proliferated after that. Everybody kind of just wanted to make sure that they had as many weapons as they could have. And so the question was like, how do we go about like maneuvering our way through this complicated world where, again, we have these ridiculously powerful weapons of mass destruction, and others have them as well. Our ideological rivals have them as well, and at any point they could launch their weapons, and so game theory was kind of used to kind of figure out what is the best way of sort of assuring that we don't blow each other up, but we are able to maintain our position without, losing any ground to the rival. And so ultimately it was determined that the best way to do that is to have as many missiles as your rival does, and just always have the threat of mutually assured destruction, which the acronym for that is MAD. So MAD was the outcome of this sort of analysis, where it just became clear that if the threat of annihilation of the entire planet was always present, then nobody really had an incentive to launch any missiles. And it's a sort of a simple sort of thing that you can just come to terms with on your own, just thinking about the situation. Like, yeah, that makes sense. But, obviously it wasn't clear cut to everybody, because even though things are sometimes logically clear, like you have irrational people in the world that with power, as we now see very clearly, and that can always lead to like irrational outcomes, right? And so, that's why you have experts and whatnot kind of figuring things out with their special tools like game theory. Actually, the funny thing is that a lot of this stuff was kind of worked out here in California, in Santa Monica, at the RAND Corporation, and you might have heard of it. It's a government think tank, fairly conservative, but that aside, like it does like kind of research work. RAND used to stand for Research and Nuclear Development. Now it just stands for Research and Development. But yeah, that's sort of the place where a lot of this stuff was worked out. Anyway, so that was one application of game theory, and of course, economists also have incorporated this approach into our analysis of our interdependent decision making by firms in these oligopoly markets. And so that's what we're going to cover in this chapter. So first, we'll do a quick overview of games and strategic thinking, and then we'll start talking about the first case, and then we'll call it a day, and then we'll reconvene next Thursday, and then talk about like a lot of like different applications that the game theory could have within the context that we are talking about, then even not within the context we're talking about, even some other related sort of situations, and then ultimately get to more insights about how firms can escape the Bertrand trap, the Bertrand pricing trap of like having to wind up paying, charging the marginal cost and having zero economic profits. Anyway, game theory is a general framework to aid in decision making when your payoff depends on the actions taken by other players. In a game, the players are the individuals who make decisions. So in oligopolistic markets consisting of two firms, so in duopolies, which is the case we'll consider throughout the chapter, each of these firms have to make pricing decisions, let's say. So then the firm managers are the players in the game. The decisions of the players are their strategies. So if a manager can either choose to have a high price or a low price, those are their strategies. The payoffs to the players are the profits or the losses that result from the strategies. And due to the interdependence, the payoff to a player depends not only on the player strategy, but also on the strategies employed by other players. All right, so in the analysis of games, the timing in which the decisions are made is important. So in a simultaneous move game, each player makes decisions without knowledge of the other player's decisions. They make the decision at the same time. So the Kuno setting is a simultaneous move game, essentially. In a sequential move game, one player makes a move after observing the other player's move. So again, the Bertrand oligopoly setting has that kind of characteristic to it. So that is a sequential move game in a sense. It's also important to distinguish between games played one time versus repeatedly. So there might be situations where firms engage in competition once, setting prices once, or there might be situations where they're repeatedly engaging in competition, and therefore always have to be considering what the rival is going to do. So in a one-shot game, the underlying game is played only once. In a repeated game, the underlying game is played more than once. Quick example, suppose that there's two gas stations located side by side on the same block so that neither firm has a location advantage over the other. The consumers view the gasoline at each station as perfect substitutes, and will purchase from the station with the lowest price. The first thing in the morning, the manager of a gas station must phone the attendant to tell him what price to put on the sign. So it's a pricing game, simultaneous move, repeated, but every day it happens in the morning. Since the manager must do this without knowledge of the rival's price, this pricing game constitutes a simultaneous move game. I need to fix this over here. So this type of game is often called a Bertrand duopoly game. So given the structure of the game, if the manager at Station A calls a higher price than the manager of Station B, then consumers will not buy gas from Station A, obviously. The manager of Station A, therefore, is likely to reason, I think I'll charge $9.50 per gallon, let's say, which would be lower than maybe what Station B would charge. If Station B thinks that the manager will charge $9.50, then they will charge $9.49. So then the manager thinks, given that they'll probably respond in that way, I should maybe just charge $9.48 instead of charging $9.50. But then the manager could think, well, if she thinks I'm going to charge $9.49, or maybe she thinks. So if manager B thinks that I think that she'll charge $9.49, then she'll trick me by charging $9.47 instead. So that might be something that might run through the manager's mind, like the fact that the opponent is operating the same way that she's operating. So then the manager decides, well, maybe I should then charge $9.46. But then she thinks, but if she thinks that I think that she thinks, so anyway, like that is sort of like the kind of thinking that one can engage in that could, again, result in them ultimately just pricing down to marginal cost, because that's the only logical result. So game theory is a powerful tool for analyzing situations such as these, and it can, again, provide insights into how firms can not wind up in these situations where they're just like, based on the nature of the competition, ultimately getting themselves to charge marginal cost. All right, so let's look at the case of the simultaneous move one-shot game. That's the last thing we'll cover today. All right, so again, a strategy is a decision rule that describes the actions a player will take at each decision point. So when the players are making the moves simultaneously, so you have a simultaneous move game, the game can be represented as a table, and that has a name. It's called the normal form representation of the game. So the normal form game representation indicates the players in the game, so you have player 1 and player 2, the possible strategies of the players, and the payoffs to the players that will result from alternative strategies. In this example, there's 2 players. Generally, player 1 will be represented on the column, and then player 2 will be represented on the row here. The players can be any 2 entities that engage in a situation of strategic interaction. So it can be the U.S. and Russia. It can be let's say wolves and foxes. Biologists tend to use game theory as well to sort of figure out like how equilibriums are established in nature based on competition amongst animals between predators and prey. All right, so player A has 2 possible strategies. They can either play up or down. So player A's strategies are represented by the 2 rows here. The feasible strategies for player B are left or right in this case. So the strategies for player B are represented by the columns. The payoffs to the 2 players are given in the entries in the cells within the matrix here. So each cell has 2 numbers. The number on the left represents the payoffs for player A, and the numbers on the right represents the payoffs for player B. An important thing to notice is that the payoff to player A crucially depends on the strategy chosen by player B, so interdependence, right? So if player A were to choose down and player B were to choose left, then player A would wind up with -10 and player B winds up with -7. But if player A were to choose down and player B were to choose right, then obviously player A would wind up with 10 versus -10. So again, their strategy is chosen by them, but the outcome is chosen based on what the rival does as well. So if player A's strategy is to play up, while player B's strategy is to play right, then player A is going to get 15 units of profit, let's say. And then player B is going to make 8 units. Since the game is in a simultaneous move one-shot game, the players get to make one and only one decision, and they have to make their decisions at the same time. Also, the players cannot make conditional decisions. Well, I'll choose up, but if they choose right, I'll choose right. I'll choose down instead of up. Like they can't make those kind of conditional decisions because everybody's making the decision at the same time. What the optimal strategy should be for a player in this type of game can be complex and depends on the nature of the game being played. So definitely there's uncertainty in these situations. So there's ways of us using this approach to kind of minimize that uncertainty by identifying certain characteristics of the game that can give us indications of how firms should best go about engaging in behavior, and also what the likely outcomes may be given the nature of the payoffs, given the nature of the strategies. So one instance in which it's easy to characterize the optimal decision involves what's called a dominant strategy. A dominant strategy is a strategy that results in the highest payoff regardless of the action of the opponent. So if one has a dominant strategy, they will play that strategy no matter what their opponent does, and that will always result in the highest payoff for them. So the dominant strategy for player A is to play up in this case. So let's identify how we can figure that out. So in order to figure out if a player has a dominant strategy, you take the perspective of the player and you think, what would player A do? In this case, we're taking the perspective of player A. What would player A do in response to player B playing left? Well, if player B plays left, I can either play up or down. If I play up, I get 10. If I get down, I get negative 10. So obviously, it makes sense for me to choose up. As a player in this game, I understand what everybody can do and what the payoffs are. So I should also consider what I should do in response to player B playing right. So if player B chooses right, then I can choose up. I can choose down and get 10 units, or I can choose up and get 15 units. And obviously 15 is better than 10. So I'm going to choose up as well if player B were to choose right. So regardless of what player B does, player A's optimal choice is always to play up, and therefore player A has a dominant strategy to play up. No matter what the opponent does, player A is always going to play up. That is their dominant strategy. So if we can identify a dominant strategy for a player, that obviously provides some insight into what they should do. All right, so that gets us to the principle. Play your dominant strategy. Check to see if you have a dominant strategy. If you have one, play it. Quick demonstration problem. In the game we've been analyzing, the question is, does player B have a dominant strategy? So again, to figure out if player B has a dominant strategy, we take the perspective of player B, and then we figure out what player B should do in response to player A, each of their possible strategies. So, in response to player A playing up, player B can either play left or right. What should player B do? Left, right? Left will get B a payoff of 20, which is greater than 8. So 20 is better. In response to player A playing down, what should player B do? Right, because 10 is better than 7. So the question is, does player B have a dominant strategy? No, right? Because they're not going to play the same strategy regardless of what their opponent does. They're going to play different strategies depending on what their opponent does. Obviously, they are making their moves at the same time, so they can't react to what their opponent does. But the fact is, like, they've identified they don't have a dominant strategy, so they don't have that extra sort of amount of certainty that they can gain from the situation by always playing their dominant strategy. Yes.
So wouldn't the dominant strategy
So you're saying the dominant strategy for B to play left because you think that player A would choose down? Okay. All right, so that's the next thing is to like acknowledge that even though you may not have a dominant strategy, that your rival may have one, and so you need to take that into consideration. So yeah, you're ahead of me, but thanks. That's good. I'm glad you thought of that. Anyway, the point of this example is just to be able to again take you to the paces of being able to identify whether or not a player has a dominant strategy or not. And we see that player B does not have a dominant strategy. So player B does not have a dominant strategy. So when a player does not have a dominant strategy, it might be an option for them to play what's called a secure strategy. So in the case in which a player does not have a dominant strategy, one possibility would be to play a secure strategy, a strategy that guarantees the highest payoff given the worst possible scenario. So essentially they look at what is the worst case for them in each option based on what their opponent might do, and then minimize that by choosing the lesser of the two evils, essentially, which is what all of us should have done in November. All right, so by using a secure strategy, a player maximizes a payoff that would result in the worst case scenario. To find a secure strategy, a player examines the worst payoff that could arise for each of his or her actions and choose the action that has the highest of the worst payoffs. All right, so in the game we've been analyzing what is a secure strategy for player B. All right, so if player A were to choose up, player B could either choose left or right. If they choose right, that would obviously be the worst outcome for them. If player A were to choose down, then player B again would either choose left or right. Obviously, left has the lowest outcome, so that's the worst case scenario for them if player A were to choose down. So we see that those are the two worst options for player B. So obviously, playing right would maximize the worst option for them. So the secure strategy for player B is therefore to play right. That minimizes the worst outcome for them. So again, they don't have a dominant strategy, so an option is to play the secure strategy. And this is how you identify a secure strategy. Make sure you know how to identify a dominant strategy, a secure strategy. All right, so the secure strategy by player B is right. Secure strategies, of course, suffer from two shortcomings. One, it's a very conservative strategy and should be considered only if you have a good reason to be extremely averse to risk. So if you just don't want to take any kind of chances, like this is the course you should take, but you know, some risk is necessary in business. It does not take into account the optimal decisions of your rivals as well, and thus may prevent you from earning a significantly higher payoff. So if you haven't thought about what your rival's likely to do, then you're not really thinking the game through thoroughly enough. So player B should recognize that player A has a dominant strategy, and that their dominant strategy is to play up. So assuming player A chooses a dominant strategy up, player B will earn 20 units over 8 units by choosing left, but only 8 by choosing the secure strategy. So obviously it would make sense for the player to take into consideration what their rival is likely to do and choose left versus play their secure strategy. Again, given that they don't have a dominant strategy and are just kind of trying to figure out what they should do. So a natural way of formalizing the end result of such a thought process is captured in the definition of what's called the Nash equilibrium. So a set of strategies constitute a Nash equilibrium if, given the strategies of the other players, no player can improve her payoff by unilaterally changing her own strategy. The Nash equilibrium is basically a set of strategies that exist in a game or may not exist in a game or may exist several times in a game that no player has any incentive to deviate from. And the way you identify a dominant strategy in a game is by going through each player, figuring out what they would do in response to their rival, and then in the places where those options overlap, based on, again, going through both players and choosing their optimal choices in response to both of their opponents, will be a Nash equilibrium. So where the two choices overlap, so we'll go through examples, of course, and you'll see, A will always choose up. So these are the ones they'll choose, and then B will choose left if A chooses up, and then right if B chooses left. So this is going to be wind up being the Nash equilibrium for the game, because this is the choice that both players have no incentive to deviate from. They would both choose that strategy, and therefore they would both wind up there. So a brief history of the Nash equilibrium. John Nash is a mathematician, smart guy, also economist, worked at MIT for a while, was a schizophrenic, so he was a bit crazy, ultimately realized the voices in his head were just him in his head, and got a little better, took some drugs, got back to work, died last year in a car accident. But he did establish this notion of a Nash equilibrium early on. Actually, it happened, I think, late in college for him, and then he won the Nobel Prize for it a lot later. And basically what it did was it kind of changed the approach of economic theory, because with the notion of a Nash equilibrium, we were able to identify likely outcomes in situations that had this kind of interdependence and uncertainty. So by identifying Nash equilibria, we were able to give some insights into how things are likely to go in these type of complex situations. And so we were able to make real world predictions, whereas prior to that, we were only able to make kind of theoretical, hypothetical predictions. But we can analyze actual situations with game theory using the notion of a Nash equilibrium to say, well, this is likely to happen because of the fact that we've identified a Nash equilibrium. So that's where the name Nash equilibrium comes from. And it's a really powerful concept. Obviously, it's not super powerful based on, like, the simple sort of example that we looked at here, and we will look at. But again, it did somewhat change maybe even the world, depending on how you look at the impact of certain research approaches that have been taken that have influenced policy. And there will not always be a Nash equilibrium. Sometimes there will be multiple Nash equilibria. So, it's not always clear cut. But again, if you can identify a Nash equilibria, then essentially you can identify a very likely outcome to these type of complicated situations. All right, folks, we're done for the day. Good job getting through another lecture. Have a good week. Again, we're not meeting on Tuesday, so I will see you next Thursday. And that's it. Have a great one.